Hello and welcome back for another presentation. This one on the Introduction to Earth's Dynamic Lithosphere. So this will be a two-part series in a sense. The first one, as you're watching now, will be about introducing the reasons why the Earth is dynamic. And then the second presentation that will follow will introduce some of the faulting and plate tectonic type portions as well. So let's kind of jump right in. Excuse me. So it's kind of like a lava lamp. So let's kind of go back to the beginning. As mentioned in other presentations, we learned a lot about Alfred Wegener, who was a climatologist who proposed the theory of continental drift in 1912. Not much was known then. A lot more was then observed and interpreted, especially during World War II when we started looking underneath the oceans. So I picked this idea like a lava lamp, if I hit play. Due to the radioactive decay of isotopes at the Earth's core, you have heat that is being given off, right? Anytime that there's energy involved, the resulting piece will be heat. So in this case, you've got the center of the lava lamp, which is a light bulb. The wax is being heated up. As it absorbs the heat, it expands and then starts to float to the top. As it gets farther away from this heat source, when it gets up to this region at the top, it starts to cool down. And once it begins to cool down, it will shrink and condense and start to sink back down. So you create these convective currents in a sense. So what we see, what the presentation is saying here, is that because of this decay of the center of the Earth and the core, you see temperatures, exceeding 11,000 degrees Fahrenheit. That being said, that heat rises and sinks, and since you have this process going on over and over and over of these convection cells, you essentially create the fuel and the energy needed to move whatever's floating on top of it. So I picked this diagram here in the bottom left one. It's essentially showing that you had a pot of water, and you had two little wooden blocks sitting on the water, and then you turn the heat on, and then you start boiling the water, and it starts to make the bubbles, and the air kind of comes up and creates that circular motion. In doing so, those wooden blocks would start to bounce around and move away from each other, and that's really essentially the driving force of this. Some fun facts. Again, this is molten material. We call that magma. It's underneath the Earth's surface. Once it's been pushed out onto the surface, we call that lava. And most of the lava that we see or observe is between 1300 and 2400 degrees Fahrenheit. So it's incredibly, incredibly hot. This here, as we'll make reference later, is very much like a conveyor belt, very much like those the little rack at the grocery store, and a little plastic thing comes by when you're checking out and moving all of your stuff, your goodies that you're going to purchase along the way. So in one area, it's being pushed because it's growing, and then somewhere else it's going to get lost. And we'll talk more about that in a moment, but really we live in this dynamic place of creation and then also of destruction. And you have a lot of this refreshing. So there's not a lot of really old material available to see because you have this recycling that's occurring. So let's look at the layers of the Earth. So here are very fundamentally, very simplistic, our layers of the Earth. So I'm going to start from the bottom, the internal part, and move our way outward towards the continental crust. And we'll spend a little more time looking at each one in a moment. So we have a solid inner core. Temperatures range, they're between 10,800 to 11,000 degrees Fahrenheit. And as we see, as we get farther away from the core, it begins to cool down a little bit. I mean, obviously, we're still looking at the tremendous amounts of heat, but it does cool down. So then we have a liquid outer core, which is about 7,000 degrees Fahrenheit. Then we have our mantle zone, which is kind of complex. We have a lower and an upper mantle zone. That's between 4,500 up to the top is more towards 1,800. And then we have this asthenosphere. There should be an H there, it's awkward. Asthenosphere, in that sense, what it is, it's kind of like a plastic zone. It's really like a protective area that allows crusts to exist without having to remelt. Then we have our oceanic crust and our continental crust up on top. We live within the lithosphere, so that's everything that we can live on, right? So we'll go through each one of these layers. The interesting part about your crust that we have oceanic and continental, they're very different material. Oceanic crust is predominantly basalt, and continental crust is predominantly granite. And they are very different, not just by appearance, but also by its chemistry. We find that granite has larger crystals. We also find that it's a lot lighter in sense and weight. We find that the oceanic crust, which is predominantly basalt, is a lot denser. Also has very small crystals. There's also attributes of cooling that we talk about later in minerals and rocks. So now that we went from bottom to top, let's go from top to bottom. So we'll kind of take through each one of these pieces. So the first part is Earth's crusts. We have two. We have oceanic and continental. So what we have here is that these are some of the thinnest layers that we have within our slice of the Earth. We find that the continental crust, again, is granitic. It's between 5 and 70 kilometers in depth. It just kind of depends on the region. Obviously, if you have areas where you have large mountain ranges that have been pushed up, your crust will be a lot thicker. If you're looking at a place that's had extreme volcanism, perhaps places like I don't know, Long Valley Caldera in California, or maybe Yellowstone National Park, you'll find that the crust is significantly thinner there because a lot of it has already been kind of blown up in that sense. Our oldest crust is about 4 billion years old, and we find that it's a lot more buoyant because, again, it's that granite. It's a lot lighter. It's not as dense. Now, our oceanic crust is basaltic. It's about 3 to 8 kilometers thick. It's about 180 million years old, is the oldest that we're observing, just because, again, it's being recycled and it's very dense. So what does that mean, dense material? Well, in this diagram that I'm showing you right here, the oceanic crust in this diagram is moving towards the right. And because it's dense or heavier than our continental crust, it's able to subduct, which means it's able to go underneath. So imagine you have two books and you're slamming the books together. A couple things will happen. If they're of equal density, in most cases, they'll push and they'll pop up. Mountain, right? That's how you do mountain building. But in this case, we find that since the oceanic crust is denser, it pushes and pushes, and one will go under because it's heavier, and then the continental crust is up above. Well, now that you're taking all of this material and pushing it back under, it begins to remelt, which will add fuel to those cells, which essentially create a volcanic range. So we saw that, well, looking at other presentations that we've talked about, we know that we have the Pacific and the North American plate, but between them was one more. It was called the Farallon plate, spelled with an F. The Farallon plate was subducted underneath, and now both the oceanic and continental crust are now meet. But you certainly had a third plate that was stuck in between, and that's why we have this volcanic range. That's why we have the Sierra Nevada. That's why we have part of the Cascades, and so on and forth. So those are our crusts. Our next layer will be the lithosphere and the asthenosphere. So the lithosphere is known as a region that includes the crusts, which is both oceanic and continental, but will also include the uppermost mantle. The asthenosphere is a semi-rigid part of the mantle that flows like hot asphalt. So it is a liquid in a sense, but it's more like a putty. So it is molten, but it's not like water. It's very dense and it's like putty, really, and it moves very, very slowly. The fun fact, the deepest that we've ever been able to drill down successfully is about 7.6 miles, which really isn't that far. I mean, think about 7.6 miles from where you are right now. I mean, for me, 7.6 miles from my house would be Six Flags Magic Mountain, which, I could walk that if I wanted to, but I'd rather drive. So here's a diagram. I just kind of expanded the previous ones. Now we can start seeing, okay, oceanic, we have continental, this zone here, all of this is really part of the lithosphere, and the asthenosphere is kind of that layer in between that kind of allows us not to remelt, and, allows us to have that crust that persists, but it's also very fluid in the sense that it's able to move. All right, so we'll keep moving down. Let's look at the mantle. So this is the largest and thickest layer that we've observed. It is, oh shoot, see, that's what happens when you make your own PowerPoints, is that you have spelling errors. It is made of very hot, dense rock. So it is rock, but it's able to move very slowly due to convective currents. So again, we have that inner core, outer core. This is not to scale. That heat rises and then it cools down, so then it will sink. And so we again have this circular motion, like I showed you with that lava lamp a little earlier. The movement of the mantle drives these tectonic forces, which can also then drive volcanics. So in this sense here, you have two areas where it's pushing up. We have essentially it's being forced away from each other. So you're going to create a ridge between there. And it's not uncommon to have what we call fissure eruptions. Fissure eruptions is when the earth is pulling apart and it's just a wall of lava that shoots out of the oceans or out of the crust itself. Fun fact again, the mantle zones make up about 67% of the Earth's mass. So it's a really, really big zone that we can study. Granted, we're not able to really, we've never really been down that deep as we now know. So a lot of questions often come from like, well, how do we even know about any of this? If we can't see it, how do we know what's happening? We know that there must be molten material because we see a volcano erupt, but how do we know what's really going on? And we're able to do that by looking at wavelengths. Different types of waves are able to transfer through liquids and some cannot. Some can transfer through rock, some cannot. And so that gives us an idea as to how deep these certain areas are, because when you send a wavelength down, it will bounce when it finally hits its farthest point. It will bounce back and will allow you to kind of measure that distance. And then the core. We have two cores. We have the inner core, which is made of solid iron and nickel, and then we have an outer core, which is made out of other metals, but more of a liquid state. So again, the inner core is what's having that radioactive decay. It's decay essentially of uranium, and the uranium will then turn into lead. We use that in radiocarbon dating that allows us to look at half-lives and to be able to understand age lengths. The outer core is made out of liquid. It's the result of that heat. So I am using this image to kind of paint a picture in a sense. These are different salad dressings. It's the best I could find. Um, these salad dressings, as you're observing them, I mean, you're looking and going, oh, there's all kinds of weird stuff. There's some, green onion in here. There's oil. There's vinegar. There's chili flakes, whatever it might be. But notice how they're starting to settle, and when they're settling, they're separating, right? Well, they're separating based off of the density, right? So vinegar, oil, water, salt, pepper, all these things have a different density in which they'll settle within themselves to create layers. And that's really how I look at the layers of the earth in the same way, is that, because of the different amounts of heat, different minerals are going to be distributed amongst these areas within these densities, and then it kind of separates in that sense. So when we're looking at different layers of the earth, like we say here, the inner core is made of solid iron and nickel, and then we can look at the outer core, which is going to have other metals and minerals within it. We're able to know that there's a difference because of their density and where they're going to be moved. We find that also silica, which is the main element other than oxygen and quartz, that silica is very light. It will float more towards the top where it separates, and that's where we'll talk more about that later when we look at rocks and minerals. So again, to kind of paint that picture that we have these different layers of the earth, we can go from inner core, outer core, lower mantle, upper mantle. Then we have the asthenosphere, the lithosphere, which includes oceanic, and then continental crusts. So you have this nice little slice of the earth that gives us this opportunity to understand these different layers. And again, why is this important? Well, all of this whole picture of the layers of the earth is the driving force for plate tectonics. So now that we understand that there's different layers, we understand that there's heat involved, we understand that there's an energy, and we know also there's convection currents in which things are in motion. Now that we know this, now it starts to make sense, right? Now we're supposed to go, okay, now I see why these large continents are able to then be moved around our planet at a rate, about the same rate on average as your fingernails grow. It's about 1 inch or 2.54 centimeters per year. Granted, you don't sit there and watch it move all at once. It takes a whole year for those to move, but we see that energy is there. We're able to then, plot it with GPS and see how things change. Now, that being said, knowing that plate tectonics occurs, and now that I've told you the rate in which it moves, you're like, well, that's not very fast, right? Well, it's not, but it is if you think about it, because geologically, time is very different. We're here for a very, very short period of time versus the length of what the planet has already experienced. So put it this way, plate tectonics move. So that means our plates will move, 1 inch a year, which means in the human lifetime, the average human lifetime, plates move about 6 feet. So think about how many generations. Maybe maybe you can go back 3 generations of people in your family. That's 3 different lifetimes, right? So that's 18 feet that things have moved. So when you start putting it in that type of perspective, you start thinking, wow, that's crazy. There's a lot of big differences in how things are moving. Then we get more into it a little bit as to how we know some of this, but we also have plate boundaries. So now that I've kind of made this painted this picture that there's motion and lots of things are very dynamic, we have very large plate boundaries. So when I think of plate tectonics, I think of going to like a swimming pool, and you have a bunch of kids that have those rafts, those big foam square rafts that are floating around. So they're all moving in different directions, but they will then bump into one another. And because of that energy of them bumping, maybe this raft comes this way and bumps into this one and causes it to go that way. Because of this energy that's amongst these different rafts, that's what we're seeing here as plate boundaries and plate tectonics. So we have three dominant boundaries that we can observe. We have what we consider constructive. So if I hit the little play button, notice what happens to them. They're separating, right? They're diverging. We call that constructive because you're making new crust. So in this case, this is an image showing a rift zone in perhaps somewhere in the mid-Atlantic or something like that. But you're having that conveyor belt coming up, separating and moving along its way. So you're creating new crust. So that's why it's considered constructive. Another one, I'll stop there. Another one we'll have is conservative. Well, conservative means you're not making and you're not breaking. So it's technically just pushing and sliding back and forth along one another. Okay, so this is very traditional of a strike slip boundary or a transform boundary because it's not making anything new. It's not ruining or destroying anything that was old. It's literally just bumping and sliding. I'll hit pause there, and then we have destructive. Destructive, notice what happens. They're pushing together, right? They're converging. So they're not diverging, they're converging. There's different ways this can occur. Remember, I mentioned earlier taking two textbooks and ramming them into one another. If they're of equal density, if you push, 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 they'll probably pop up. And when they do that, you make mountains, right? Like the Himalayas. Or in this case here, we can see that you have them pushing together and maybe the oceanic plate will subduct. And when it subducts, it melts and then it's lost forever, right? It's recycling itself. That's why it's considered destructive. So we have divergent on the far left, you have strike slip transform in the middle, and then you also have convergent on the far right. So you can think of it as a dance move. They pull apart, they slide together, or they move into one another. They move in and they go under, so they're still converging, but one subducts, and we call that subduction. So hopefully this makes sense so far. Well, let's kind of put it together. Super complicated diagram, totally get it, but we're going to be able to very quickly kind of tear it apart. So we know that we have this puzzle of many, many pieces that are all moving in different directions. So we have prominent plate boundaries that have been drawn. So if you notice, most of the plate names represent the country that's on them. So you have the South American plate, you have the North American plate, you have the Indian plate, you have the African plate, the Australian plate. So we have all these different names that distinguish these boundaries that we have. Now in this diagram, there's a lot of different colors. To just kind of put it in perspective, we see that the blue lines, it's like a dark, like a navy blue, represents convergent zones or reverse faults. We find that there's little red polka dots that are all over this map. Those are all volcanic centers. We also see areas that are red. Red zones represent actively spreading or diverging zones. So if you think about it, if you see my mouse right here, I'm looking over here at the Nazca plate. So knowing that this boundary here is causing, see the arrows, it to move away. So if this rock is moving to the right, it only makes sense that it's going to crash into the South American plate, right? Because you notice on the right-hand side of the South American plate, again, you have another ridge that's moving towards the left. So really, South America is stuck between two ridges that are moving towards each other. Well, that's why we have an area here with tremendous mountains. Same thing with looking at the Indian plate. You can see the blue little lines here. It means they're being pushed together. That's an area of convergence. So we can see these red zones are pushing it that way. So there's arrows. Again, this is really complicated, and I absolutely understand that. But I wanted to be able to show you really looking at a global perspective of everything, right? So I hope that this is overwhelming in a sense, but I hope that it makes sense. You can start to see that there's patterns. It's like, oh, so this is moving away. This must be squished together. If this is moving away, it must be squished together somewhere else. Africa's a mess. It's got stuff pushing all over the place. It's pushing up in here. Well, even looking at this, right? Let's move right down here. This is the mid-Atlantic ridge. So we have this big line. We know that everything, either left or right of it, is moving away. Well, we know that now. So now it makes sense that if everything was reversed, that South America, Brazil would very nicely fit into here. That we would see that parts of North America at some point could fit very nicely in areas up in here. We start to see all these patterns and designs. You know, when you look at a globe or look at a map, if you could just cut out the continents that were there, you could probably find a way to squish them together to make one big piece, knowing that they were in motion and within their direction. Well, this is why we now know this. This is why it's not a question anymore, because we know that things are constantly in motion. So let's simplify this diagram to like this. I think this is about as simple as I can make it. So we have red, which is convergent, white is divergent, and then pink is transform, which is also known as strike slip. So we can see here as an example. This is an excellent example. This is the San Andreas Fault. So here we have the Pacific plate, we have part of the North American plate, you have your Caribbean plate down here, the Cocos plate, all these different plates. So you should be familiar with these, right? Because this is what drives our planet, this is what creates our landscapes. And then to understand what's happening with this diagram allows us to understand where we have been and where our continents are going. So we start to understand a better picture of this. Again, you can see there's a pattern, right? So knowing that white is divergent and red is convergent, it makes sense that they're near each other, right? So knowing that this mid-Atlantic ridge has a mixture of divergence in some areas that it kind of moves along, it's more conservative or transform. You know, that there must be areas of red around it, because at some point, you know, it's just like, again, going back to that pool, you're in your raft. If I push your raft, you're going to hit someone at some point. You know, it may not be for a while, or it could be right now, but at some point, your raft is going to bump into someone else. And so that's kind of that mentality that I use when I look at this. Now, I've mentioned this whole thing that when things were together and far apart. Let's talk about that real quick. So these are just our last three supercontinents when we know that, you know, these large land masses were together. So I'm going to go oldest to newest. So the oldest is Gondwana. It's often referred to as Gondwana land, and that was between 596 and 578 million years ago. So here we can see that you have South America nestled very nicely here with Africa, Antarctica, and Australia. What's interesting is this little piece right here, the FLA. That's Florida. So actually, Florida was part of Gondwana land. It wasn't until things moved around that Florida actually was then attached to North America. So then we move forward, and now we have Laurasia, which we see that Gondwana has now merged with Laurasia, which is North America and Asia. So then we have this meeting together, and then when they're fully together, we call that Pangea, or Pangea. I've heard it pronounced in many different ways. Pangea. I always call it tectonic spooning. That's when everything was together. So we can see that you know, Florida is now being attached to North America. This is where you see most of your story, right? You know, you've all heard of this. But I wanted to take a little bit farther. So we have Laurasia and Gondwana. At one point they were separate. You know, it was separate for quite some time, about 100 million years, and then it merged into Laurasia, where it then merged into Pangea. So you can start seeing this sequence. So I guess the next question is like, okay, so this sounds good. So we've got these three: Gondwana, Laurasia, and then Pangea. Perfect. How do we know this? Well, lucky for us, you know, we know that there aren't a lot of old rocks because of weathering and because of just the fact that it's being recycled. But we do have, in some areas, an excellent fossil record. So it's going back to Alfred Wegener. So utilizing the 1912 theory of plate tectonics, as well as the observed fossil record, scientists are incredibly comfortable and confident to understand the different origins and locations of which we were. How do we know this? Well, as an example, here we can see that there is this line, this ridge of rock material that also shares this fossil record. And so that means they find the same fossils here that they found here. They found this guy here, that's a Triassic fossil record. merge within all three of these pieces. So we can already put the continents together based on their shape, but then we start finding these different flora and fauna of the fossil record that also merge. Now, remember going back into minerals and rocks, we understand that rocks are, it's like baking, right? Very special recipe. Just because you have the ingredients doesn't mean it's always going to turn out. There's a very special heat that's involved, there's a very special balance. So when we find a very specific type of rock, it is, and we find it, another one that's 2 or 3 thousand miles away, we know that they had to have been together at one point because the variation is just too hard for it to be separate, to be two different events. We know that there must be some commonality, right? So think about like DNA, right? You do those DNA tests and you find someone that you're related to in some other country, and you're like, well, I don't even know these people. Well, it means there must be some lineage. At some point, your parts were part of a whole. So we start to understand this, and that really helps us, this fossil record. Now, we started seeing this fossil record going back 200 years ago. We didn't have dates involved then, but we understood that it's like, well, we found these fish fossils or trilobite fossils. We learned that they were freshwater. There's no way that they could have swum the ocean to both sides, right? So there must have been a freshwater lake that was between them at some point, which would have been something that would have been more inland after perhaps a glaciation or of things of those sorts. So for us to be able to understand this really helps paint that picture. So, where are we? Well, we understand that we have layers of the Earth, and we understand that due to the radioactive decay of isotopes, in particular, that heat is being given off. It helps us make material molten. It creates those convection currents, and that's the driving force of plate tectonics. Now we're able to take the information we know now, and using GPS units to trace where we're going forward, we were able to take that to go backwards, and we were able to take a fossil record and to merge them together to now understand, okay, this is where we were, and this is where we're going. And then who knows? We can even project. There are people and scientists that are working towards projections. And there's been a lot of discussion that very far down the line, that there will be a point, again, where we see this tectonic spooning, where all of these continents will merge together again. I mean, think about it. If I go back to this diagram here, if this is the mid-Atlantic ridge, if you're flying from, the East Coast over to, say, I don't know, maybe somewhere in Spain. At some point, who knows? It might actually be faster for each to fly this way around the Earth, all the way around, right? No, instead of going this way, it might be faster to go the other way, because as essentially North America and Europe are moving away from each other 1 inch a year. So somewhere down the line, not just thousands, millions of years from now, maybe even billions at that point, it might actually be faster for people to travel going the other way. Isn't that crazy to think? Well, I hope you enjoyed this. Be sure to hang around for the next one, which starts talking about faults and boundaries. I'm super excited for that one because I'm going to use a model to show you how things move. That being said, I appreciate your time. Don't forget to subscribe and like to the channel, and we'll talk soon.